Welcome to this video lecture. My name is Dr. Girraj Sharma. I am Associate Professor at the Department of Electronics and Communication at JCRC Foundation. So today we are going to discuss about this topic strain gauge in the chapter transducer in the subject electronic measurement and instrumentation. The course code is 4EC306. Now before going to start this topic, let me briefly introduce to you what is a transducer. A transducer is a device which converts non-electrical quantities into an electrical quantity. For example, a microphone used to convert audio signal into an electrical signal, which can be a voltage or current. There are various types of transducers, out of which strain gauge is one of them. Strain gauge is basically used to measure strain, and it can convert pressure, force, or displacement into electrical quantity. So let us first discuss what is a strain. Strain is the ratio of the change in any dimension reduced in the body to the original dimension. There are various types of strains, out of which a longitudinal strain is defined as the increase in the length per unit original length when body is deformed by any external force. Now, strain can be negative. If we compress the body, then stress will be negative. If we expand the body under tensile forces, then strain will be positive. Now, practically, the magnitude of strain is very small. Hence, it is often known as microstrain. In this diagram, if a tensile force is applied, the length of the wire changes from L to delta L. Hence, the longitudinal strain is defined as delta L by L. Now, what is strain gauge? Strain gauge is a device which is used to measure strain of an object, and it is often used in load cell, which is again a type of transducer. It is a passive transducer since there is no active component used in strain gauge. Hence, it is a passive transducer, and it will require an external power supply because it cannot generate power on its own. It was invented by Edward E. Simmons and Arthur C. Rugg in 1938. The most common type of strain gauge is known as wire strain gauge, which is a insulating flexible backing which is supported by a metallic foil pattern. Now let us see what is the typical construction of a strain gauge. This is an example of wire strain gauge in which it consists of a small diameter wire. The diameter is very small. And now this wire is attached to a backing material. Generally, this backing material is made up of plastic or bakelite. This wire is looped back and folded several times to create an effectively longer wire. Since the change in the length is very small when compression or expansion is applied to a wire, hence we require longer wires. And now to save the overall space, this wire is back and folded several times. The longer the wire, the larger the resistance. Hence, the larger the change in the resistance with applied strain. This is the working principle. Now, let us see what is the working principle of strain gauge. It is based on the fact that resistance of the wire changes when the length of the wire and the cross section of the wire changes. We know the expression of the resistance is equals to rho L by A, where rho is the resistivity, L is the length of the wire, and A is a cross-sectional area. When a tensile force is applied, it increases the value of length. It increases the value of length, which is there in the diagram. It increases the value of the length, and hence the resistance also increases with this. And on the other hand, if compression is applied on the strain gauge, the length of the wire reduces, hence the resistance of the wire decreases. Now we know by this expression that resistance depends upon the length. It also depends on the cross-sectional area, but we are not dealing with this now. Hence, if we take length under consideration, we can say that the resistance is directly proportional to the length. Hence, if the length changes, resistance changes. So on this fact, the working of this strain gauge is totally based on. Now, if a metal conductor is stretched or compressed, its resistance changes on account of the fact that both the length and diameter of the conductor changes. The sensitivity of a strain gauge is often defined in terms of a parameter known as the gauge factor. Later, we'll define what is a gauge factor. Now, in order to derive expression for the gauge factor, let us consider a metal conductor. In this metal conductor, the original length was capital L and the diameter was capital D. And if we apply a tensile force F in this direction, then the original length changes from L to delta L, and the diameter also reduces. Suppose the change in the diameter is delta D. We know what is the original resistance of this metal conductor. It is equals to rho L by A. Now let us suppose this equation to be equation number 1, R is equal to rho L by A. If the tensile stress is S is applied to the wire, it will result in change in the length delta L. It will also result in change in the cross-sectional area delta A and change in the diameter delta D. So if we partially differentiate this equation, R is equal to rho L by A with respect to stress S, we'll get this expression in equation as an equation number 2. Now, if we divide this equation throughout with this value of R, which is rho L by A, we'll get this expression in equation number 3. In this equation number 3, there are 3 factors on which this value change in resistance is depending. The first factor is per unit change in length delta L by L. The second factor is per unit change in cross-sectional area delta A by A, and the third factor is per unit change in resistivity, which is delta rho by rho. Now we also know that the cross-sectional area of this wire is equals to pi by 4 d square, where d is the diameter. If we again partially differentiate this expression with respect to S, we'll get this equation in equation number 4. And if we divide this equation 4 both sides with capital A, we'll get this expression 1 upon A del A by del S, which is given by equation number 5. We can put this value in equation number 3 so as to get this final expression in equation number 6. Now we'll introduce a new parameter which is known as Poisson's ratio. We know what is Poisson's ratio is. It is the ratio of lateral stress divided by longitudinal strain, which is minus del D by D divided by del L by L. So from this expression, we can define what is the lateral stress, which is del D by D, which can be determined by using equation number 7. We can put this equation number 7 in the previous equation 6 in order to get this expression. Del 1 by R del R by del S is equals to 1 by L del L by del S plus V multiplied by 2 by L del L by del S plus 1 by rho del rho by del S. Now, if the variation is very small with respect to stress, we can substitute these values del R by del S with delta R, del L by del S with delta L, and del rho by del S with delta rho. Hence, we can get this expression delta R by R is equals to delta L by L plus 2V delta L by L delta rho by rho. Now, we can define gauge factor as the ratio of delta R by R divided by delta L by L, which is defined as the ratio of per unit change in the resistance to the per unit change in the length. Now we know what is per unit change in the length. It is longitudinal strain, which can be defined as epsilon. So it is delta L by L. Now we can put this value, to get this value, we can divide this whole equation by delta L by L. So finally we can get this value GF, which is equals to 1 plus 2V plus delta rho by rho divided by epsilon, where epsilon is delta L by L. So finally the gauge factor comes out to be 1 plus 2V plus delta rho by rho divided by delta L by L. Now if we neglect the effect of resistivity here, if the change in the resistivity is very small compared to change in delta L by L, we can neglect this whole quantity del rho by rho divided by delta L by L. Hence, the final expression for the gauge factor is equals to 1 plus 2V. The gauge factor is equals to 1 plus 2V is only valid when the piezoresistive effect, that is, the change in resistivity due to strain, is almost negligible. So we have already discussed it that del rho by rho can be neglected if only the piezoresistive effect is negligible. Now, for the metals, the value of Poisson ratio lies between 0 to 0.5. And for other materials, we can determine the value of gauge factor from this table. Now, let us solve one numerical problem based on this formula of gauge factor. The problem is the resistance wire strain gauge uses a soft iron wire of small diameter. The gauge factor value is given as 4.2. Now, in this question, it is given that we can neglect the piezoresistive effect and we need to calculate the value of Poisson's ratio. We know that the value of gauge factor is equals to 1 plus 2v plus del rho by rho divided by epsilon, where epsilon is longitudinal strain, delta L by L. Since the piezoresistive effect can be neglected, we can neglect this quantity del rho by rho divided by del L by L. Hence, the final value of the gauge factor is equals to 1 plus 2v. Now, in this value, in this equation, gauge factor is given as 4.2. So we can put this value 4.2 and finally can calculate the value of Poisson's ratio, which is equals to 4.2 minus 1 divided by 2, which is equals to 1.6. Now let us see what are the different applications of the gauge, strain gauge. Now strain gauge can be used to measure pressure, it can be used to measurement for force, and it can also measure small displacements, and it can also be used for measurement of torque and loads. So we'll stop here. Thank you very much.